he defined Chomsky normal form, and in that grammar, every rule either has a non-terminal goes to two non-terminals, or it has a non-terminal go to a single letter. And we won't go into how to do it. I could even make it a homework assignment. It's not very hard how to convert any grammar into Chomsky normal form. All right. So it also allows from the start symbol you can have the empty string if that's how you want to end. All right, so the advantage of these grammars is that they're easier to, they're worse than the look-ahead one grammars. Those are great. Those you just parse in linear time. These, we're gonna come up with an algorithm now for it that parses in n squared time. When the string that you're parsing is of size n, the algorithm is n squared. Now, right, so this is just saying there's an algorithm which converts grammars into non-context-free, non-Chomsky normal forms into Chomsky normal form, but we're not gonna do that. What we are going to do is we're going to look at this n squared algorithm, n cubed algorithm. Now, let me give you a little. No, that doesn't take much time at all. That's easy. What we're doing now is we have a Chomsky normal form grammar, and we're given a string to parse. Say this string here, that's the input, and the output is a tree that's parsed. All right. Now, let me give you a little heads up before we go into this algorithm. All right? This algorithm is an example of what we call dynamic programming. And I've been maintaining since I started here in 95 that we should teach 3101 before we teach 2001. And why is that? Well, because dynamic programming, we spend about 2 weeks on it. And the hardest algorithm that we do in 3101 is this one right here. Oh, wow. All right, so kind of let this roll over you, but don't get too frightened by it. All right. And just like fairy godmothers and bumping lemmas and stuff, I bring my own talk into it. I talk about birds and friends, and hopefully I can sort of explain what those birds and friends are. One advantage is if you happen to take 3101 from me next term, then you'll be warmed up. All right, so here's the recursive algorithm. All right, the problem is, here's why we don't do a recursive algorithm. We don't do a recursive algorithm because we're parsing from T, and we don't know whether to call get A, get C, or get T. And if we call get T, then it would recurse forever, right? So we're kind of stuck there. And so what we do is I like to pretend that we have a little bird who knows the answer, and she gives us little hints. Now the truth is, we never have a little bird, and what we're going to have to do is we're going to have to try everything that she might suggest, right? But really, the little bird is just a way of saying, what are the things that we're going to try? All right? So the question we ask her is, well, there are 3 rules coming out of get T. Which of the 3 rules do we do first? And which rule are we using here, right? And she's going to, let's pretend that she told us to use this rule. Now, as I say, in reality, we're going to have to try all 3, but the one we're trying right now is this one. All right, so she tells us that. And then We have friends, and who are friends? Friends are really great guys. You can give a friend any instance that's smaller, and he will give you the answer. All right? So, well, what do we want from our friend? We want the left parsing from our friend. Right? So what do we have to give our friend? And we have another two friends. One friend gives us the left parsing, and one friend gives us the right parsing. Right? Now, what do we have to ask our first friend? Well, we have to tell him that's what we want from him. So what do we ask? We give him this instance. We want to start from C. We want you to parse this down here. Right? And if we were to give him that, then he would be really happy and he would give us the answer. Right? And then, but the challenge is, we don't know where to split the input, our input. Right? There's some place it's split. Well, this part is coming from C and this part is coming from A, but we don't know where that split occurs. All right? So what we're going to do is, in my language, what we do is we ask the bird where to split. But really what we're going to do is we're going to try all those places to split. All right? So suppose we ask the bird, and the bird says, use that rule and use that split. Right? This is what we're trying now, is to use that rule and use that split. And so then we can ask how many answers are there that she could give us? Right? Well, the number of first rules is how many rules are here. In this case, it's 3. The number of rules for T. How many places to split there are there? Right? Our string is of length n. Right? So there's n plus 1, n minus 1, something like that. Doesn't really matter. Places to split. Right? So what's the total number of answers she might give? Do we add those or do we multiply them? Right? We multiply them, right? Because we have to try every possibility here with every possibility there. Right? So we're going to try all of these possibilities. Right? And when we're trying one of those possibilities, what we do is we ask our left friend, we say, left friend, parse this for us, and and he doesn't have to recursively do it. Actually, it's going to be table lookup. That the solution is already going to be saved in the table, and he's going to look it up in the table and give us the answer. And then we ask our other friend, and for this sub-instance, and this friend looks it up in the table. Right? And then we take our two friends' answers and we combine them into our answer. Right? Does that make sense? So here's the code, but we're not going to get too scary on it. What it does is, we have a bunch of sub-instances. We loop over the sub-instances. We loop over the bird answers, and we ask our friends. But we'll get into that more when we teach 3101. So now we want to think about what are all our sub-instances that happen. Yes? Cost. The cost of was, in this case, yes, it is a good parsing, or no, it's not a good parsing. That's the cost. So you're getting too far ahead of us. So what are we doing here is, I have my instance, right? And then I ask my friends about their instances, and I ask the friends about and their friends ask their friends who ask their friends, and so forth. So there's all these sub instances, right? And we want to see, it's just like, this is a different problem where we look at what, a set of sub-instances. Don't worry about that picture. Don't look at that picture. All right? It looks kind of funny. Their arms have changed color, and his belly has changed color. Why is that? And his mouth has gotten bigger. Sometimes PowerPoint just gets scared and freaks out. But we'll have to remember to delete this picture because it's only going to scare you guys. Anyway, how do we determine the set of sub-instances? We just say my friends, sub-instances. So if this is my instance, I'm starting at T, and I'm going to this string down here, then who are my sub-instances going to be? They're going to be Well, I'm going to start with some other letter, and I'm going to have some split. So maybe this will be my friend's subinstance. And his friend will have this subinstance. So how many subinstances are there in total? Well, a subinstance starts with one of the many non-terminals. We have some non-terminals. And it begins at some I and it ends at some j. So the number of these, right, it begins at some t. And so we start from t to and start at ai and end at aj. So how many such subinstances are there? It's the number of non-terminals times number of non-terminals times n squared, right? The number of i's times the number of j's. So we construct a table for all these subinstances. So here we have a subinstance for every non-terminal t, and for every I and for every j, there'll be an instance which stores. Is this just flowing over everybody? Yeah, for sure. It'll flow over everybody, and then I can say, yeah, it's good. All right? It'll give you some flavor of how this algorithm goes. All right? We have all these subinstances. We store them in the table. And what's the total running time? The total running time is you have to solve each subinstance. You loop over all subinstances, and when you're solving a particular subinstance, you loop over all bird answers, and so then the running time is that. So you got a question here?
Can you please backtrack on some slides and re-explain the subinstances, please?
Yeah, let's do subinstances here. So if I'm given this, what is an instance? An instance is a terminal that you start with and is a string that you're parsing. Right? That's as an instance. And how many instances are going to arise in my friend's friend's friends? You're not going to get a completely different string here. Right? The only strings you're going to get is it's going to be the start symbol will be one of the non-terminals. And the string that you have to parse is going to be a subsequence. It's going to start at some I and go to some j. Right? Yeah.
What do you mean by bird answers?
I told you, as I said, it's the bird answers are the things that we're going to have to try. So the bird is going to tell us which rule to use. She'll say, use this rule, and she'll tell you where to split. So don't worry about this too much. We're supposed to cover parsing. It's funny, in fact, the amusing thing is I'm quite sure on this syllabus, maybe I should go back and check, that we're supposed to cover this one, but we weren't supposed to cover the look-ahead one grammar parsing, and I think that one's beautiful, and this one, it's just going to scare you. All right? So the running time, let me tell you one more last sentence. The number of subinstances, remember, was the number of non-terminals times I times j. And the number of bird answers was the number of rules times the number of places to split. So assuming the grammar is of a fixed size, then the running time is n cubed.